Hi everyone. Our topic for today is parallel image processing and computer vision using CUDA, NVIDIA's GPU framework. My name is Kartiki and today I will give you a brief outline of the topics we are going to cover. We start with understanding the traditional GPU implementation. Next, we learn about what GPU and CUDA is and move on to understand the CUDA architecture. We then move on to understand the advantages CUDA has over the classic shader-based model. Next, we get a brief understanding of the use of CUDA in digital image processing and computer vision and its application in these fields. We then explore two popular algorithms, the Sobel edge detection and the Gaussian blur algorithm, to perform the tasks of edge detection and blurring in image processing. For both these algorithms, we take into consideration their serial as well as parallel implementations and improvements in their performance with parallelization of these algorithms using CUDA. Finally, we summarize our work by stating how parallel processing using CUDA is an ideal solution for image processing and computer vision related tasks. Moving on to the traditional GPU implementation, by tradition, the shader-based framework was the basis of GPU programming. The framework, however, had a number of disadvantages. Vertex transformations or pixelized illumination mapping had to be done for the algorithms. The framework itself had a steep learning curve and a robust knowledge of pipelines and their rendering, and also a background in graphics programming was required. Shader-based programming, which was originally meant for graphics-based programming, does not have random memory access for writing of data. The data needs to be transformed into texture maps. We have to operate on the data as if the nature of it is texture-based. The total number of branch statements or loops that can be used is limited. This made it difficult for GPUs to be used for the general purpose computing tasks. NVIDIA's new programming framework, CUDA, was launched in 2007 and supported seamless general purpose computing on GPUs. The GPU is considered as a co-processing device to the CPU. GPU executes high volume of threads in parallel and has its own memory, DRAM or device memory. In terms of parallelism, chunks of data that can be executed in parallel are executed on many threads as kernels in the GPU. Moving on, CUDA organizes the threads running in parallel as blocks. The blocks are logical in nature. There is a mapping of each block to a multiprocessor located in the GPU. There is an inter-block synchronization within the parallelly executing threads. The threads communicate with one another. Blocks are further organized onto grids, and each grid has a number of blocks. Intra-block synchronization is not possible, neither is communication a possibility between them. But threads existing in the same grid are organized in such a way that they execute the same piece of GPU code. Now, programming in CUDA is of hybrid nature. For CUDA programming, one needs to run the programs on two types of devices or platforms mainly. One is the host system, and the next is the device system. Now, the host system consists of CPU as well as the main memory. The device has the GPU, which has CUDA capabilities and the supporting architecture. Now, the source code of CUDA consists of a mix of two types of code, which are both executed on the host as well as the device. Here is an overview of the CUDA architecture that I just explained. As you can see that the host has two kernels, while the device has the grids and the blocks. The blocks have multiple threads which are executed in parallel. Now let's have a look of the advantage that CUDA has over the shader-based model. Since CUDA is based on the C programming language, the need to understand the shader-based API is eliminated. This significantly reduces the learning curve that programmers have who are already well versed with C. Now, CUDA possesses random memory write and read ability. Also, CUDA has a memory hierarchy that is flexible. Another advantage that CUDA has is that the cache memory present between the global memory and the processor core can be shared between them. This is what we mean by flexible memory hierarchy. Moving on. In computer vision and image processing, the same computations take place repeatedly, and data parallelism can be exploited in such scenarios. The SIMD, which is the single instruction multiple data architecture of the GPU, is hence suitable. Digital image processing is the field of adjusting the properties of the image to fine-tune the image and produce a high-quality image. Some of the popular techniques used for digital image processing are edge detection, blurring for noise reduction, etc. The main purpose of using digital image processing is to manipulate images to get the desired output. Next, we will explore in detail some popular digital image processing techniques like edge detection and noise reduction using popular algorithms and explore details of their implementation using CUDA GPU parallelization. Moving on, the Sobel edge detection algorithm. Edge detection is when we use matrix math to calculate areas of different intensities of an image. Areas where there are extreme differences in the intensities of the pixel usually indicate an edge of an object. After finding all of the large differences in intensities in a picture, we have discovered all of the edges in the picture. Sobel edge detection is a widely used algorithm of edge detection in image processing. Sobel is one of the most popular edge detection algorithms used in today's technology. When using Sobel edge detection, the image is processed in the X and the Y directions separately first and then combined together to form a new image, which represents the sum of the X and Y edges of the image. However, these images can be processed separately as well. This will be covered later. When we use a Sobel edge detector, it is first best to convert the image from an RGB scale to a grayscale image. Then from there, we use what is called kernel convolution. A kernel is basically a 3x3 matrix consisting of different or symmetrically weighted indexes. This will represent the filter that we will be implementing for edge detection. When we want to scan across the image in the X direction, for example, we will want to use the following X direction kernel that you see on the left-hand side to scan for large changes in the gradient. Similarly, when we want to scan across the Y direction of an image, we can use the Y directional kernel to scan for large gradients as well. By using kernel convolution, we can see in the example image that there is an edge between the columns of 100 and 200 values. Now that we have gone through all the mathematics of the edge detection algorithm, it is now time to put it to use on a real image. Now, can you see the image that I am showing? The first step to be done in the Sobel edge detection algorithm is to convert the image to a grayscale. While it is possible to use the algorithm in standard RGB scale, it is easier to implement in a grayscale. Now this is the conversion of the image to grayscale. Now we can move on to the next step. We see the differences between the Sobel edge detection in the X direction and Sobel edge detection in the Y direction separately. As we can see, the images are fairly similar simply because many of the edges in the images are at an angle. However, we can see that in Sobel Y direction, it does not catch a lot of the leg of the chair on the right. That is because when we use the Y direction, we are scanning from top to bottom, and it will only detect edges that are horizontal in the image. On the other hand, Sobel X direction will detect the edges of the chair leg because the image will be processed from left to right using a different filter. Now this image that you can see is when the two filter results are added together to create an accurate representation of all the edges, the X direction and the Y direction in the image. Moving on. Let's have a look at the parallel implementation of the Sobel edge detection. From the figure on the left, it is observed that the two critical tasks in the algorithm are grayscale image and edge detection. These two blocks are accelerated using the GPU by using CUDA. The two tasks are implemented in parallel using multi-threading on a FPGA board. Parallel execution significantly reduces the execution time of the algorithm. Multiple pixels are worked on in parallel by the different threads to convert the image into grayscale first, and then similarly perform the tasks of masking and magnitude calculation tasks of Sobel for edge detection. The shared memory, which acts as a buffer between global memory and registers, is used for the computation. It is observed that the execution time with usage of shared memory decreases drastically as against without the usage of shared memory. Now, as it is observed from the second graph, the algorithm performs significantly better when executed on a GPU. Most significant time reduction is observed in the task of image grayscaling and edge detection, which were implemented on the CUDA-enabled GPU and using CUDA programming paradigms. Moving on to our next algorithm, which is the Gaussian blur algorithm. Now, the Gaussian blur algorithm, which is also known as Gaussian smoothing, is a classic algorithm for blurring images. To put it very simply, the Gaussian blur algorithm is a process of performing a weighted average operation on the entire image. The value of each pixel is obtained by gaining the weighted average of itself and other pixel values in the field. Blurring can be understood as taking a pixel as the average value of its surrounding pixels. As you can see in the image, the center point will take the average value of its surrounding point and it will become 1. From a value perspective, it is smoothing. On graphic, it is a blur effect. The center point will lose its detail. You can see that in the image. The question now is, if every point will get the average value of its surrounding points, then how should we allocate the weight? If we just use simple average, it's unreasonable because images are continuous. The closer the points in distance, the closer the relationship between the points. Hence, the weighted average is more reasonable than simple average. The closer the points in distance, the larger the weight. Normal distribution is an acceptable weight distribution model. You can see the normal distribution curve. If you see on the screen, you will be able to see the density function of normal distribution, f of x. The density function of normal distribution f of x is also called as Gaussian function. The one-dimensional format is as shown on the screen. Here, mu is the average value of x because center point is the origin point when calculating the average value. So consider the value of mu to be equal to 0. Hence, we get the following modified expression as you can see on the screen. This was a brief about the density function used in the Gaussian blur algorithm. Now let's move on. You can see 3 images on the screen. I will now briefly explain the weight matrix calculation for the Gaussian blur algorithm. Okay, now let's start with the first image. Assuming the coordinate of the center point is 0, 0, then the coordinates of the 8 points which are nearest to the center is as we can see in image 1. Moving on to the second image. Now, to calculate the weight matrix, we need to set the value of sigma to 1.5 in this expression. Once we set the value of sigma to 1.5, then the weight matrix is transformed as seen in image number 2. The sum of the weights of these 9 points is then calculated, and we can see the sum of these 9 points in the third image. The sum approximates to 0.47. This was the weight matrix calculation. Now moving on to the implementation of the algorithm. Let's get to the actual calculation of Gaussian blur. Using the weight matrix that we calculated previously, we can calculate the value of the Gaussian blur. Now, if you see the image on the left, here we are assuming that the gray values of the pixels range from 0 to 255. As you can see, each pixel in that image has a value from 0 to 255. Now, if you see the image on the right, that is the output of our Gaussian blur algorithm. Now, each point in the image on the left multiplies itself with a weight value that we previously calculated in the weight matrix. Once the multiplication operation is done, we can see an output as seen in the image on the right. Basically, our image is now successfully smoothened or blurred. Now let's move on to the parallel implementation of the Gaussian blur algorithm. Now some key points in the parallel implementation. The Gaussian blur algorithm makes use of the properties of kernels that are running in parallel in GPU CUDA programming. The Gaussian algorithm is implemented on the host device architecture that we saw previously by effectively utilizing the kernel functions to invoke the threads in parallel to perform its tasks. Now, by changing the grid and the block sizes, the number of threads required for parallelization are determined. The tasks are then processed in parallel, and this significantly reduces the time required for execution. The optimum number of threads, blocks, and grids is found out using a kernel function. Let's see the performance of the Gaussian blur algorithm when it is executed in parallel. The following two images show the GPU execution time and speed up in execution time respectively for a 1024 cross 680 resolution image when the Gaussian blur algorithm is implemented on it. Now, as you can see in both the images, we can see a significant performance increase both in the GPU utilization time as well as speed up when CUDA is utilized for this blurring. You can see a mapping of number of threads versus time in the first image, and you can see a mapping of number of threads versus speed up in the second image. In the first image, you can see that the time is significantly reduced in the parallel implementation. And in the second image, you can see that the speed up has significantly gone up. That means our algorithm has sped up quite a bit when we use the parallel implementation of this algorithm. So a parallel implementation is indeed successful in our case. Let's move on to our final part. Let's see some key conclusion points in our paper for the day. Nowadays, graphics cards are in huge demand for a wide variety of applications. Those applications are 3D applications as well as gaming applications. Programmable interfaces. The programmable interfaces that we now have, they have made this a possibility for general purpose applications like image processing and computer vision. CUDA is beneficial for image processing applications due to its parallel implementation capabilities. Most of the operations in image processing tasks have work that is repeated again and again. Hence, CUDA is beneficial in such scenarios. This kind of tasks make CUDA a perfect way to implement these algorithms. In a way, these kinds of tasks perfectly fit as a use case for CUDA, as CUDA utilizes its threading and multiprocessing capabilities. Now, these tasks are computation intensive, but super easy to apply parallelism on. That is one more reason why CUDA is good for these kind of tasks. These algorithms are mostly individually implemented algorithms, and hence there is not too much interdependence. Now, since there is no interdependence or less interdependence, it makes it correct for CUDA level parallelism. One more point is that data allocation within the threads is generally a critical task in any parallel algorithm, as the efficiency of the algorithm improves significantly due to this task. Also, the memory and its bandwidth is important and should be taken into consideration before implementation. Now, all in all, CUDA is thus an inexpensive solution which provides a massively parallel architecture for data parallelism in tasks that are related to image processing as well as computer vision. That was my concluding statement. And thank you so much for your time.